All right, good morning. Today we're going to talk about chapter 3 of our top hat, which is about the different various states of matter that things can go into. So we're going to be talking about matter instead of energy, and basically that can be in one of three common states, either a gas, a solid, or a liquid. And we're going to talk about that today. So as I said, there's three different states of matter: the solid state, the liquid state, or the gaseous state. And those are states of matter that any type of matter can be in. So what those three states of matters have is they have some rather distinct properties about them, which allows them to have certain behaviors that you associate with each type of state. So for instance, when you think of a solid, you kind of think of a certain kind of rigid thing, maybe a little bit denser type of material, but very, very fixed shape, very set properties, not very compressible. And those states are very different than the states you might think of for a liquid, which is very fluid, very motionable, very different, or a gas, which is very different than both of those. And each state has very distinct properties. They have distinct properties of density, distinct properties of a shape, how fixed that shape is, whether it's flexible or not, how compressible those states are, and then also expansion, how much they contract or shrink when they heat up or cool down. And you can see from this image right here, just three examples of either a solid, a liquid, or a gas. And you can see that the different types of molecules are in different orientations in those distinct states. So in the solid, everything's very close together. The molecules are physically in contact and they're holding on to each other and they retain a shape. Liquid molecules are still in contact, but they're able to roll around each other. And the gas state, there's no contact between the molecules, which allows them to expand to fill up the container that they're in. So the first thing we're going to talk about is density. Density is the mass per volume of an object, and it's something we've talked about before. Again, density is just the mass of something, m, divided by its volume. And when you look at the density of an object, that's going to be a pretty distinct property for every object. Every object has a density that you can calculate. You can calculate how large it is. You can calculate its volume, its area, its width, its height. You can put it on a scale. You can measure its mass. And then you can figure out the density. And usually matter that's solid has the highest density than any other state. So solid densities have very, very high densities. Liquids also are pretty dense. And then the gases usually have the lowest state. So the gases usually have the lowest state of matter densities. And that's because gases can expand. They'll take up the entire container. Solids have very rich, rigid location, very rigid structure, and they're usually, all those molecules are confined to be touching each other. But then when you look at the gas molecules, those gas molecules are very far away and they're not touching each other. And that generally makes the volume of the gas very large for the same amount of mass, and then a very, very low density because you're dividing a number by a very large number down here, a very large volume, and that makes your gas very, very low density because you're dividing by such a large number. So that was one of the properties that the molecules have. Another property that molecules have is their shape. Shapes are fixed for a solid versus a liquid. So if you think about something in the solid state, right, a very fixed shape, look at your computer in front of you, your phone in front of you, any of the chairs you might be sitting on or the floor you're standing on, right? Those are very solid objects, very fixed shape. They don't move when you step on them. They don't move when you touch them or hold them. Versus something like a liquid, the shape will change and it'll adjust to the shape of the container. So if you look at something like this bottle right here, the liquid in this bottle is shaped a certain way, and it's bottle shaped. If you were to pour the liquid from the bottle into the spoon, it would go from being a bottle shaped liquid to a spoon shaped liquid. As the liquid moves from one container to the other, the shape changes of the liquid. Liquids will always take the shape of their container, but liquids have a fixed volume. So you can see here again, the liquid line right here, the liquid doesn't expand anymore. It can't take up the entire bottle because the liquid doesn't have enough volume to fill the whole container. Gases will. Gases are interesting. They'll take the same shape as their container like a liquid would, but they'll also expand up and fill the entire container. So gases have very flexible volume. They could be either very dense gas like the one up here, or they could be a looser density gas that's taking up the whole container. Another example here, you can see that initially the gas is all in one container with this stopper kind of blocking it, so the gas molecules are able to move around but not leave. As soon as we open up that stopper, the gases leave from one container to the other. They fill that container and they take up both volumes. So the gas's density has gone down as it takes up a second location and fills up a larger container. And as that expands, the gas expands to take up both containers. Gases will always expand to completely fill their container. And you might notice that even with bottles of perfume or bottles of scents, right? You open up that lid, you take off that lid, within a few minutes, you'll smell that gas as that gas goes from filling up the bottle right here to filling up the entire room as they expand to fill the new container, which is the room. So we've talked about shape, densities of gas, we've talked about the shapes of the gases. You know, if you think about why can molecules change shape, why can solids not change shape, why can gases change shape, that all has to do with the forces that are holding those molecules together. Those molecules are held together by forces that hold the molecules, not the atoms within the molecules, not the carbon connected to the hydrogen, but that molecule together is going to be interacting with other molecules. And solids have really, really strong forces between those molecules holding them together. Solids are held together very strongly. And that results in solids having a very fixed shape. Those molecules don't want to move. Those molecules don't move to other places in the lattice. They stay together. Those molecules hang on to each other very tightly. They don't move around. So those molecules are in a fixed position. That means that solids have a very, very fixed shape. Liquids still have pretty strong forces between the molecules. They're still hanging on to each other, they're still touching, but the molecules can kind of roll around each other. So it's like if you had a bunch of tennis balls in a bag, and think of that as a liquid, right? The tennis balls are still touching each other. If you lift the bag up, the tennis balls all go together, but then if you put it down on the floor, the tennis balls can kind of spread out and still touch each other, and that's like a liquid in a container. They can move around, they can roll around, and they're still touching each other, but they're not taking on any fixed shape. They take on whatever shape the container gives them. So that's an example of how liquids can change their shape, but they still have a fixed volume because no matter what you do, you can't have more tennis balls. You're not going to have more tennis balls or less tennis balls in that container. So the liquid's always going to have the same amount of tennis balls. So the shape, even though the shape changes, the volume stays the same. But gases don't have to worry about changing, have fixed volumes, and gases don't have to worry about fixed shape because in the gas, all those molecules are very separate. So rather than having a bunch of molecules that are kind of close together like this, gases, they're all very far apart and they're actually not touching each other. So in a gas state, like here, all the molecules are very far apart from each other. All the molecules don't touch each other. And because of that, the molecules are very far apart, no cohesive forces at all between the molecules, and they're free to move around every which way. And every single molecule is free to move in a different direction, which means that the gas molecules are really far apart from each other, they don't really touch each other, and they don't really touch any of the containers that they're in. So they're able to kind of move around until they hit the wall. So they move around, this molecule is going to go here, it hits the wall, goes somewhere else. This molecule goes all the way down here, hits the wall, goes up here, hits the wall again, goes somewhere else. Those molecules are always moving around and they're kind of expanding, moving around. That means the gas takes up all that space. The gas has all this area to take up. So the gas takes up a very large volume right here. You can see gas taking up a really big volume versus the solid or the liquid, the volume is confined kind of to the area that the molecules are touching each other. So you get a really different kind of shape. You get gas behavior where gases can expand, take up a whole container. Gases have a very low density, again, because of this low force between the molecules. Gases don't have a fixed shape because of this molecule. So these are all different properties of gases, all because these molecules are far apart and not contacting each other, no cohesive forces between each other. And that ability for the molecules to touch each other, that cohesive force between the molecules, also means that solids and liquids and gases have a certain degree of how compressible they are. So if you think about a solid or a liquid where all the molecules are pretty much touching each other, there's not much space between the molecules because they're already touching for you to put another molecule. Versus if you look at a gas with lots of space, we have all this other available location to put new gas molecules. So gases have a lot of space between the molecules, and we could keep putting more and more gas molecules between them until we got down even to a solid, liquid or solid state. But there's lots of space between the gas molecules, which means there's lots of space to put more and more gas molecules in. And that's why if you look at how compressible or how much you can push on an object, gases have a very high compressibility, significantly higher than the rest of than either the liquids or the solids. And again, that's due to the fact that gases have such a low density. Their container has a lot of gas molecules there, but there's lots of space between those gas molecules, and there's a lot of empty space that a new gas molecule could be pushed into, or an existing molecule could be pressed down and put into. So if you think about a balloon, and you try to hold the balloon or you try to squeeze a balloon, right? What happens? You squeeze a balloon, the balloon kind of moves around a little bit. The gas can get compressed a little bit. Or even just filling a balloon. When you inflate a balloon, you're taking air from your lungs, you're pushing it into the balloon, and you're putting a lot more air into the balloon than would normally be in that space. And if you want to prove to yourself that you have a lot more air in that space than you would normally have, well, fill up a balloon and then let go, because all that extra air is then going to leave the balloon and the balloon will fly away from you because you put more air than was normally in that amount of space. You've compressed that air into a smaller space, and you've gone from a state more like the green to a state like the green and the blue. The green is the air that was normally there. The blue is all that extra air that you pushed into that balloon. And that puts a lot of gas molecules in a small amount of space. You've compressed that gas. Same thing happens if you have your gas grills at home, or if you go to a barbecue. Gas grill like that, propane tank like that, what they do is they take a gas and they put lots and lots and lots of gas molecules all into a container like this. And that's a gas under a lot of pressure. And there's a lot of pressure in that gas to hold all those gas molecules in a very small space. You can't really do that, on the other hand, with a liquid or a solid. So solids and liquids have a very low compressibility, not very compressible molecules right there. And that's because the liquids and the solids don't have much space between them. They're already pretty tightly packed, right? If you try to put another molecule between these molecules that are already touching each other, there's no space for another molecule. There's not space to really put another solid molecule right here or here, because we've already got the molecules as close as we can get together. And because of that, you can't really push any more liquids into the same space. So if you tried to push more liquid into this bottle, it's just going to come back out because the bottle's already full. Or if you try to put more rocks into this bottle here, they're not going to hold any more because this bottle's already pretty full. You can't put more rocks into this bottle. Solids don't compress the same way that gases do. And that's why molecules in the liquid and solid state, because they're so close together already, you can't really put them any closer together. They have a very low compressibility, but gas molecules have lots and lots of space between them to allow those molecules to kind of compress together even closer together and still remain a gas for a good amount of time. You have to compress lots and lots and lots of molecules together to go from a gas back to a liquid. So even if you compress a gas a couple hundred times stronger than it normally would be, you're still going to remain in the gas state. You're just going to be a little denser gas than you normally would be. And then the last property of gases or liquids is how much these things can expand or contract if you change the temperature. And temperature does change with volume. So volume changes with temperature. So if you take a liquid at hot temperature or a liquid at low temperature, the volume does change a little bit. And if you want to try this at home over the next few days, you need to get a really accurate measurement, like an really accurate cup measuring cup or things like that, or a volume flask. And if you take one of those and you put liquid that's really, really cold, so not ice, but fairly cold liquid, freezer temperature almost, and then you heat it up, and you heat it up in your very slowly over time, and you have a very fixed volume to begin with. If you heat it up to almost boiling temperatures, you'll note that the temperature, the liquid volume will be a tiny bit higher than it was before. And that's because liquids in the warm temperature, high temperature state do take up a slightly larger volume than liquids in the low temperature state. So if you had a bottle full of water at a certain temperature that was really cool, and then you heated it up, you would watch that volume go very slightly high, but it's not very significant. Solids do expand, liquids do expand, but nowhere near as well as gases do. Gases really expand a lot. So if you take a balloon at room temperature right here, and you cool it down in something like liquid nitrogen, it's going to get really, really tiny. It's going to really contract. Gases really are sensitive to temperature changes. Gases get smaller and closer together and lower density as they cool down, and as they heat up, they expand. And you can check this with your air tires in your car. So it's a relatively cool bit warmer day today. If you were to check the air pressure in your tires, you'd get a certain number. And if you were going on a colder day, you'd get a colder, lower number. So on my car, when it was cold last week, it was about 20, 30 degrees out. And the pressure in my tires was reading about 32 PSI. And then when it was warmer again, when it got up to almost 70 degrees, so we have our temperature over here. And then when we went out to the car that day, the pressure in the tires read 38. So you can see that the pressure, which is due to the volume of the gas, went up. So the volume of the gas at higher temperature took up more space, it expanded, and that resulted in a slightly higher pressure. My tires became slightly more inflated. So gases are very, very sensitive to thermal expansion, and it's something you have to keep an eye on with your car. But this does happen with solids and liquids, so it's something you have to keep an eye on for your car with your tires. But if you notice also in this picture right here, there's also another thing in this picture, and that's this bar down here along the ground. And this is for expansion as well. So solids do expand when they heat up, but they expand over a very small amount. But what this bar is on a bridge, and bridges are very long. So this bridge is a couple miles long, and you can see these little holes right here. And these holes in the bridge are called expansion joists or expansion grates. And that's because on a cool day, this bridge is going to shrink a little bit. And if a bridge were to shrink and it was all one piece of concrete, it would crack, and that's not very good. So instead, they put these special bars in the bridge that the bridge is held together, but the bridge can shrink, and these little gaps, these little holes, will get bigger as the bridge shrinks when it gets cool. But then when it's summertime and the sun starts shining on the bridge, there's some holes here that the bridge can expand to. So you can see how these kind of lock together. So this bar here, and then this bar here. Each one of them's not touching, but there's that gap in between them. So as the bridge heats up at a warmer day, the bridge will start to expand to fill in those holes. The bridge gets larger, and then if it cools down at night, the bridge will contract again. And this is so that the bridge can get bigger without buckling or cooler without cracking, because solids do expand as well. Solids expand with temperature just like liquids and gases do, except solids, the really only way to notice this would be on something really, really large like a bridge. To be very noticeable. But your gases are going to expand the most, but solids and liquids are going to do this as well. So we can kind of think about solids and liquids and gases with a couple different properties, right? We talked about that they have a fixed shape, they have a compressibility, they have different properties. They have properties of density, they have properties of compressibility, properties of thermal expansion, properties of shape, volume, fixable or not. But then we could kind of think about, like, when you think about a state of matter, which of the kind of descriptions best describe it? Solids have a certain set of properties. Liquids have a certain set of properties. Gases have a certain set of properties. And if you were to look at these four descriptions here, you might notice that one of them describes a liquid a bit better, one describes solid a little bit better, one describes a little bit gas a little bit better. So, right, so we know that we're talking about solid here, and solids do have fixed shapes. Solids don't go changing their shape. So we can rule out these other two right away. We know it's not this one because solids are not flexible. We know that solids aren't flexible, so we're ignoring both of those. But we do know solids have a fixed shape. And in terms of how compressible things are, solids aren't very compressible because solids have all that space between the molecule, don't have very much space between the molecules. If there's not much space between a molecule, solids can't compress. So in our case here, our solid is a liquid, or a solid is a low compressible, fixed shape material. and it doesn't change too much in that regard. And then same thing, we could look at a gas. How is a gas different? So this is our final answer right here, is this one right here. So we've got fixed shape material with low compressibility. And if we were to compare that to the state that a liquid is in, or a gas is in here, we know that gases aren't fixed shape. Gases can expand to fit their container. Gases will take up the entire container. They won't take much room. They'll take up the entire container. They'll be very flexible. They can, if it's a small container, they'll fit it. If it's a large container, they'll fit it. If it's a round container, they'll fit it. So gases are very, very flexible materials. So they're not in that fixed shape category. They're more in this flexible category right here. So we can rule out those first two answers completely. But now we have to look at, is it compressible or not? And gases, again, have lots and lots of space between their molecules. So gases are highly compressible, which means that our gas is a flexible shape with a high compressibility versus our solid is a fixed shape with a low compressibility. So we've got two different kind of statements. One describes a gas, one describes a solid. And if we go to our pictures here, you can see, right, solid, all the molecules very close together, in contact with each other. Those solid molecules are not taking up any more space than they need to be to touch each other. They're very fixed because they're hanging onto each other very well. And you can see that the solid is keeping its own shape, this square type shape, even though the container has a very different shape. So this container is a triangle shape, but the solid is a square because solids maintain their own shape. It's a fixed shape, and you can't really push any more on these molecules to push them closer together because they're the closest they can already be. You compare that to the gas down here, though, very different story, right? The gas has become flexible and it's taken up the entire shape of the container. And if I were to make this container even bigger and make it a shape like this, then you would see this molecule move over here, this molecule move here, this molecule would move here. These molecules would move around, and your gas would now have a different shape. Gas would be even more different shape again, because gases are flexible in their shape. They can take on whatever shape their container has. So gases have a change in shape. And then the option of how compressible it is. Compressible, there's a lot of space between these molecules, lots of room to put more gas molecules or to push the gas molecules into a very tight container. So this is a very flexible material, but it's also a very highly compressible material as well. So those are just some properties of matter in terms of compressibility, shape, volume, density, thermal expansion. And you'll see that different states, the gas, the solid, the liquid, they'll all describe differently in terms of that. And that leads to our new, what we'll talk about next, is we're going to talk just about gases. So we're going to focus on gases for a while because gases have some properties that are pretty neat, right? The gases will expand, they'll fill their container. They have a relatively low density because of that. Again, look at all this volume right here. Very large volume over an area. So very large volume, very low mass. Here, so the mass of the molecules right here is pretty low, volume's pretty large. Because you have a low mass over a very large volume, then that means that you have a very low density, because density is just mass over volume. Here, that's because gases expand to take up their whole container. Gases are also very, very compressible because there is all this space that the gases take up that you could put either more molecules into, or you could push these molecules all down into a much smaller area and still have a gas state. So you could make this very, very compressed and still have a solid gas, more expansibility. And it turns out there's a bunch of mathematical equations that can be used to predict and model this behavior. So we can do that for these different states of matter, and we can do that especially for the gases. And there's a series of equations that can be used to predict the behavior of the different gases. So the first equation that we can use is this law called Boyle's law, which is a gas law or a chemical equation, mathematical equation, that can predict how does the pressure of a gas compare to the volume of a gas. So we've got pressure, and pressure we're going to just be using the symbol P, and then the volume of a gas is the V volume, and that'll be V. And what Boyle found when he looked at these molecules and when he looked at gases and how they behaved, what he saw is that the gases kind of had a constant pressure volume effect. So don't change the temperature of a gas, leave the temperature the same. So we're not going to change temperature, we're just going to leave temperature alone. So if we're in a room right now, we're leaving the temperature alone. If we're somewhere else, we're leaving the temperature alone. We're not changing the temperature. But what he's found is that if you left the temperature the same, the pressure and the volume were kind of related to each other. So the pressure and the volume of a gas at one condition, so with one pressure and one volume, if you compared that to the pressure and volume at a different set of conditions, so condition 1 versus condition 2, there was a relationship there. And that comes up like if you think about two different size containers of gas. So you have a gas container here, and originally the volume was at a 10-liter number. So the original volume, 10 liters here. The original pressure, 1 atmosphere here. So original pressure, 1 atmosphere, 10 liters. But if we were to change the volume of this container, so maybe this is a cylinder that we can push on and change the shape of, or something we can somehow change the shape of it. If we were to change the volume of this container and make it smaller, but leave all the gas inside, the gas isn't allowed to leave the container, but the container were to shrink. So our new volume is only 7 liters. So we've gone from a volume of 10 liters to a volume of 7 liters here. What would happen is we would see the pressure inside the container would increase because the same amount of gas is now in a smaller container. And because the same amount of gas is in a smaller container, the pressure that that gas exerts, or in a container here, how often a gas hits the wall. So if you have a gas, pressure is just a measure of how frequently the gas molecules are colliding with the walls of the container. And if you have the same amount of gas molecules in a smaller container, they're going to hit the sides of the container more often, and that means that the pressure of that gas is going to increase. Or if you were to do the opposite case, and you were to make an even larger container, now the gas molecules don't hit as often because the volume's larger for the same amount of gas, and the pressure decreases. So the pressure and the volume of a gas are linked to each other, and if you increase the pressure of a gas, you decrease the container. If you decrease the container, you increase the gas pressure. If you decrease the pressure, increase the size of the container, you decrease the pressure. And then if you decrease the pressure, the container also becomes larger. So you can check that by looking at the pressure times the volume of one state of gas compared to the pressure times the volume of the second state of gas. And you can see we did that here with this calculation right here. We just took the initial pressure, the initial 1 atmosphere, and the initial volume, the initial 10. Those are those. And then we were solving it for the final condition down here. So we have that one set here, we have the other set here, and it turns out that 1 atmosphere times 10 liters is the same as 1.4 atmospheres times 7 liters. So pressure volume at this condition and pressure volume at this condition are the same for that. And that's the same for any gas at the same temperature. As you change the pressure and the volume, they'll adjust. And we use this when we breathe. You can see an example here.